So dimension analysis is an important subject, and it is used in many useful formulas, modeling formulas, in correcting equations. So let's discuss some examples and clear the concept of dimension analysis. So dimension analysis is a technique used to study relation between physical quantities using dimensions. So let's say physical quantities. We always say this force is proportional to A, or A is proportional to force. So equating, we insert a constant. So here the constant is the mass of the object. So you see, in proportionality they have different dimension. Force has a different dimension, while acceleration has a different dimension. But when we equate it, we insert a constant which correct the dimension on both sides as well as equate them. So in this case, you see here we have the dimension of F, that is m for the mass, and meter, so length for the meter, and t square. So here the dimension is mlt whole power minus, mlt minus 2. But on this side we have only lt minus 2. So the dimension here are not equal. They are proportional but not equal. So when we equate it, we insert a constant of proportionality as well as to correct the dimension. So that means relation between physical quantities. We have two physical quantities, force and acceleration, and dimension analysis is used to relate them. They mean force and acceleration are any two physical quantities. Okay, fundamental dimensions. So fundamental for length we use L. For length we use L. For mass M. For time T. Electricity I. And for temperature K. For derived quantities, velocity L. For time, that is lt minus 1, and for acceleration lt minus 2, and for force this is ml, in square brackets, mlt minus 2. And for energy it is ml2 t minus 2. And we clearly see it because the first is very clear, that is meter per second. The second is meter per second square. The third is kg meter per second square. And the fourth is kg meter per second square and meter. This is in fact energy is force and displacement is equivalent to the work. So the dimension of the force is mlt minus 2 and the dimension of d is l, so this l is square, so ml square t minus 2, that is the dimension of the energy or work. Dimensional homogeneity. Both sides of physical equation must have the same dimension. So if the equation has two terms, one is on the left and one is on the right side, so they both have the same dimension. So that called dimension homogeneity. But if we have many terms in equations, then each term have the same dimension. Each term have the same dimension. That is the dimensional homogeneity. Example. So we see that this is a formula. You see on the left side, so let's do it. Each term has dimension L. So the left side is clear, that is distance, so L is there. Now velocity mean length per time, and t mean time. So tt cancel, we left with L, and 1 over t is constant. A has dimension L per t square, and there is t square, so t square is again, so they will cancel. So each term has L as a dimension. So this is correct formula. Newton's second law, F is equal to ma. We discussed it earlier, but you see on the left side we have dimension mlt. We discussed it earlier, so is mlt minus 2, and on the right side mlt minus 2 is okay. So that is the dimension on both sides, so it is a correct formula. So the dimension analysis, when you see a formula, you have to check the dimension of each term. If the dimension of each term is the same, then the formula is okay dimensionally. Pendulum. You see T is proportional to the product of L and G with a different power. So let we have to do it. Time period of a simple pendulum. You see we have a simple pendulum which have length L. It oscillate among the extreme. So gravity is there. So the pendulum motion affected by G and this L. So the time period is directly proportional to this L. For a large L, it has large time period, and inversely proportional to some power of the G, directly proportional to some power of the L, and inversely proportional to some power of G. So dimension analysis tells us that T is proportional. Let's say some people say that may say that mass is also affect the time period. So let include mass as well. So L has power A, mass has power B, and G has power C. Let that is the case. So the dimension on the left is T. That is time. T is time period, so that is time. So per time we take T. And let's say in bracket. Similarly, L, that is proportional. LA. Similarly, MB and GC. So this give us equation. So we can put it in dimension they are equal in dimension. So L mean length A, M mean mass, so that is MA, and G is acceleration, so this is length per time 2 whole power C. So again T and write in the brackets. So okay, all in the square bracket. So L has 2 power, L A plus C. This is B. M has only B power. And T has minus 2C. So you see we have only one power here, T. So that what that gave us, equating the power. So equating the power, A plus C is 0 because there is no L on the left side, and B is straight away 0 because there is no M on the left side, and minus 2C is 1, T1 and T minus 2. So that implies that C is minus 1 by 2. Similarly, putting this minus 2 here, so that A plus C, so that means A minus 1 by 2 is 0. So that means A is equal to 1 by 2. So what we left with, C is minus 1 by 2, B is 0, and A is 1 by 2. So putting these value in this relation. So what we did, we use the power of the dimension analysis. Power of the dimension analysis and the factor affecting the time period, and we find the value. So the formula for the time period is proportional. So L 1 by 2 because the value of A is 1 by 2, and the other is M power 0 means 0, and G power minus 1 by 2. So the T is proportional to L over G 1 by 2. Proportional. So that mean is under root. T is proportional to under root same T same. L over G is proportional, but is proportional. So how we have to find constant. So for the constant, we have to take this experiment and a stopwatch to measure the time period. So you have to take the time period by stopwatch, putting that here. You have the length and G, put the length and G over here. So you will get these values. So equating them, you have to insert some constant. One side will be larger and the other side will be smaller. So multiply the smaller one to equate with the other. So you will find ultimately that this T is 2 pi L over G, this constant. So you see how we find this 2 pi. Take the experiment as, take the stopwatch and find the time period by the stopwatch, and you have the length of the pendulum and G is 9.8 meter per second square. So put them on both sides, you will get two constants. So to equate the constant, you have to insert another constant. To equate the two values, you need a constant, and you will ultimately come to the conclusion that the constant is 2 pi in the simple pendulum case. So this is the power of dimension analysis to find the formula for the simple pendulum. Application. So application, we already discussed that we can check the dimensionality of an equation. You can unit conversion. You can also use the dimension analysis in the unit conversion. Find relation. You see them. You see that in the example. F is equal to ma, and find the dimension of the constant. So you can see that you have a constant in the, let's say, wave equation. Here is a constant and uxx. So what is this constant? What is the dimension of this constant? So when you okay, so let do it. What is this constant? In fact, this is for this fourth option, find dimension of a constant. So u has length. So ut mean, if I find the dimension of u is L, and when we differentiate with respect to time, so that is partial u partial t, so that is L over t, and another t utt, and the dimension of utt is L over t square. So on the left side we have this dimension, and on the right side there is a k, and we have to find the dimension of uxx. So ux mean partial u partial x, so the dimension of this is 1, both are length. So and uxx dimension is 1 over L, so you have to put 1 over L here. Now you see k should be equal to L square. Okay, the dimension of k, the dimension of a should be equal to L square over t square. So this is in fact the dimension of k is L over t square. L over t is the velocity, so the dimension of the velocity is L over t square. So this k is velocity square. So we can put it as k is in fact v square, velocity square. So this equation is the wave, so that is the velocity square over here. So the finding the dimension of the constant meaning this thing, you can use the dimension analysis to find this constant. What is this constant? So we find it that it is velocity, but not velocity, velocity square is here. Okay. Limitation. We cannot find numerical constant by dimension analysis. You see it in the time period case that this constant, you can find this constant by experiment, not by the dimension analysis. So the dimension analysis cannot find numerical constant. You can find that by experiment. Cannot derive trigonometric function. This is another drawback, that trigonometric function cannot be obtained by dimension analysis. Conclusion. Dimension analysis is an important tool in theoretical and applied physics. So you cannot ignore the power of dimension analysis, and it is a very useful subject in theoretical and applied physics. Okay, thank you.